All right, so I'm gonna start now, okay? Hello, everybody. This is a FTC Autonomous Programming workshop brought to you by Cubics, Wizards, and Elman Robotics. So just a few quick things before we get started. If you guys check the Zoom chat, there should be a link to something called Slido, and Slido is what we're going to be using for our question and answer at the end after this presentation ends. So please keep your questions for then. And let's get started with the presentation. So first off, we're just going to do a quick introduction from all of us as instructors.
Hi, I'm Havish. I'm the lead programmer of FTC Team 8221 Cubics. I've been the lead programmer for 4 years now, and I have lots of experience with odometry, path following, and OpenCV. And my team Cubics, we've been the world finalists for the last 3 years now.
Hey guys, I'm Sarthak from FTC 9794 Wizards.exe. I've been the software and programming lead for the last 5 competition seasons. And I've had a lot of experience with all the stuff we're going to be talking about in the presentation today, including developing a lot of training based around those things. My team, we won the 2018 Inspire Award at the World Championship, and we've competed at Worlds in the last 5 years.
And I'm Ronnie. I'm the lead programmer for FTC Team 12518, and I've been on the team for 2 years.
All right, before we get started talking about the kind of different components that go into building good software, specifically good autonomous programs, we just want to talk about the options that are available to FTC teams. So the first one I want to talk about is the most simple among these, which is the block programming language. This, as you may be familiar with, is a drag and drop programming language similar to Scratch. And while it's very simple to use, it allows you to do many of the things that you could do on some of the more advanced platforms like Onboard Java and Android Studio. And since it's a block-based programming language, there's no learning curve in terms of syntax or learning a new programming language. And since it allows you to do most of the basic functionalities that you can in Java, it's a great way for all of your team members to work on the software together and kind of help in the prototyping stages or just trying new things out on the software. And then the next 2 platforms that are available to teams are Onboard Java and Android Studio. Both of these require knowledge of Java, so you either have to learn it or apply what you already know when programming your FTC robot. In Onboard Java, this is a platform that's pre-installed onto your Android robot controller phone, which makes it very easy to access. It's web-based, so you don't have to install any additional software. And the time that it takes to download programs is really quick. I think it usually takes between like 2 and 5 seconds to do things. However, there are some disadvantages. It's a little, in terms of the user interface, it's a little difficult to use. I know it doesn't have like some of the automatic features for filling in variable names or correcting syntax errors. And perhaps the most big drawback is that it doesn't allow you to install a lot of external libraries, which is where Android Studio excels in this area. So you can install a lot of libraries like for vision and path planning, which we'll discuss later in the presentation. And in general, it has a better user interface, in my opinion, so it's easier to use in that sense. But it requires installing Java and Android Studio, the application on your computer, which can sometimes be a little complicated and cause some problems. But depending on your needs, there are a lot of options out there for FTC teams, which can help you program your robots effectively for your competition.
So next up, we're going to be talking about the differences in teleop and autonomous and relating to programming. In teleop, a lot of the error that you might have, whether it be with driving or with other subsystems, most of it can be corrected by the driver. So if your lift goes too high, it's not that big of a deal because your driver can just lower the lift a little bit. And teleop is also much more unpredictable because there's 4 robots on the field that are moving around and you have no idea what they're going to be doing at any given moment. So that's much more unpredictable compared to autonomous when there's only 1 robot which is on your line, so you have to be worried about. and it only requires automation of some subsystems, such as maybe a lift, but while autonomous requires the automation of almost every subsystem like the drivetrain. And then autonomous, you need to have a lot more consistency compared to teleop, because like I said, any error that you might have in autonomous can't be corrected by a driver. And it needs to be able to work on a lot of different field settings, which is where things like configuration variables come in handy. And it requires some more advanced programming concepts like vision and path following.
So moving on from teleop and autonomous, I'd like to just briefly go over the objectives in autonomous in the Skystone game. So one thing is delivering Skystones and delivering stones. This was one of the most important objectives this year. And delivering Skystones required you to have vision, which is something that's really important for a good FTC autonomous. Along with delivering Skystones and stones, you can also place them on the foundation with 4 points. And this is where being able to travel across the field quickly and smoothly is really important, because you had to pick up the stones from the quarry and move them all the way to the foundation, which is quite far away. And finally, we have moving on the foundation and parking on the line. Moving the foundation is relatively simple, and parking on the line is similar.
So for camera placement is actually a really important thing that gets overlooked oftentimes, because depending on where you have your camera, it's really gonna define how fast it takes for you to go to the skystone in the quarry and pick it up. Because if your phone is in a place where during initialization you can't see the block, you're gonna have to orient your robot or drive somewhere so that your camera can see the block. And if your phone can't be placed in a position where it's easy to see the quarry during a knit, you can actually use a USB external webcam and put it somewhere on your robot so that the robot can see the quarry or whatever vision target you're looking at during initialization. So as soon as you press play, the robot can do whatever it needs to do based on where the skystones are located.
So depending on how you put your phone camera, or if you're using a USB webcam, regardless of that, vision is a huge component in FTC, particularly because of how big it is when it comes to the point value in autonomous. So when Ronnie was talking about just the different tasks in this year's game, identifying and getting the skystones 10 points was 5 times the point value of just picking up a regular stone. So you can see kind of the incentive over there to complete the vision task. And as Havish mentioned, there are 2 main options for being able to detect these targets. You can use your phone camera, since every robot has an Android phone. And you can also install a USB web camera if it's too difficult to place the phone where you want it to go. But then that's just the first step. Once you have the actual hardware, you need to implement some sort of software library, whether it's one that's built into the FTC SDK or whether it's an external one. You need to be able to implement that in order to process your image, which is necessary for reliable vision and object detection. And in FTC, there are 3 main choices that you have available in order to process those images. You got TensorFlow, Vuforia, and OpenCV. So I'll start out with TensorFlow. I don't have too much experience using this personally, but one advantage it does provide is that there are existing samples in the FTC SDK. This will allow you to kind of get this running up and running pretty quickly, and you can also use those samples to kind of build off of that and take it to a higher level if you need it. One disadvantage is that it's a little slower in my experiences in terms of performance than some of the other libraries that we have. So the other libraries are Vuforia and OpenCV. Vuforia is an augmented reality library, and the way it kind of works is it takes these targets that are provided to you by the game, and it looks for different key features to identify that target. And once that target's identified, you can get an XYZ coordinate, you can get rotation and different orientation angles, which can be important for either localizing your robot or figuring out where a picture is on the screen. So if we think back to this year's FTC game, there were targets on those sky stones, and those were actually Vuforia targets. And since they were designed by the game, there are existing samples in the FTC SDK to pick up those Vuforia targets, which makes it very easy for you guys to try that out or try different things when it comes to getting the location of those targets. And since Vuforia is part of the game and makes it very easy to use. And that's the software that my team actually used this year when trying to identify where the Skystone was on the field. And then the last option, but still very popular among FTC teams, is OpenCV. OpenCV is a computer vision library that's used for a lot of different things, but you can use it in your FTC projects, and you can basically make different object detectors to look for different colors or kind of different blobs or shapes in an image. One disadvantage to using OpenCV is that it's not built into the FTC SDK, so it requires some extra effort to get installed into your program and kind of start building it up, building up the OpenCV pipeline, which can be difficult for some people because it kind of has a semi-steep learning curve, but one advantage in that sense is that there are a lot of training resources and libraries made by FTC teams that really help make this process easy. And speaking of those resources, there are a couple that I just want to mention. So there are FTC teams that have created easy ways to use OpenCV in your programming. The first one is Easy OpenCV, and the second one is DodeCV. You can see the two links on the screen over there. And then the third one, it's a QR code. You can take a moment to scan it, or it'll be later available to you guys. But that's just a video series that I developed that kind of covers how to use both Vuforia and the DodeCV library with this year's past competition season, but it walks you through getting that set up and installed into your software development platform to kind of streamline that process for you and make detecting the Skystones in this year's game very easy. All right, so the next thing we're going to talk about is odometry, and this is something that's actually very important when it comes to driving around the field and getting accurate positioning. So odometry and the algorithms calculate the position of the robot in terms of an X, Y, and theta coordinate position. And if you take a look at this CAD model over here, you can see there are 3 tracking wheels that are on the bottom of the robot. So those wheels measure the robot's position, and they calculate the robot's change in position over very short increments of time, which allow the robot to kind of accumulate that data and calculate that coordinate position. And so one advantage that odometry provides over using regular motor encoders is that they're not attached to the motors. You can see that they're just tracking wheels that aren't associated or attached to the main drive wheels. So that means that if you have wheel slippage, if you run into another robot, the odometry wheels will still measure the actual position of the robot, opposed to if you use drive encoders, if the wheels slip, the robot might be in a different position than where the robot might think it's in a different position than where it actually is. And because it works like that, it gives you extremely reliable information. It allows you to do a lot of different things with driving to different points on the field and doing some path planning, which we'll talk about later in the presentation. And if you see the QR code at the bottom of the screen, that's another video series that I worked on to teach teams how to install odometry into their robots and get the programming up and running for that. And I just want to reiterate why odometry is really important, since it allows the robot to know where it is on the field at all times. And it sets this foundation for implementing more advanced algorithms to not only move to specific points on the field, but to be able to react to different situations, have intelligent path planning algorithms, which we'll talk about now.
So moving on from what Sarthak said about odometry, another really important topic is path planning and path following. So this is something that becomes really powerful once you're able to localize properly and get your robot position on the field at all times. So path following is really useful because it lets you define smooth curves and paths for your robot to follow that are usually much faster than going to points and turning. And we're going to talk about a couple ways that you can implement this. And one of them is going to be the Roadrunner library. And this library was developed by Ryan Brott from Acme Robotics. That's another FTC team. And Roadrunner is a trajectory generation library that makes 2D trajectories for your robot to follow. And what it's really based off of is something called motion profiling. So what motion profiling is it's essentially a way of defining the position, velocity, and acceleration of your robot over a certain period of time in order to follow a certain path. So over here on the left, you can see a graph. This red line represents the acceleration of the robot, and this gray trapezoid is the velocity. So as you can see, this is a trapezoidal motion profile, and it's able to follow a really smooth path. So this blue line represents position, and as you can see, it's really smooth. And that's one of the advantages of using motion profiling, because it helps you have a really smooth acceleration and deceleration curve, and also makes your robot really consistent.
I just want to add one more thing about Roadrunner. If you just look it up, they have a lot of documentation that really helps get teams up and running with kind of setting up the library. And there's actually a quick start repository on GitHub, which if you install that onto your phones, it really helps you get the calibration process up and running quickly so your team can start using it at a relatively easy pace.
So another way of following paths and creating paths is called pure pursuit. So pure pursuit is an algorithm that takes in multiple points. Like in the diagram on the right, there's going to be around 1, 2, 3, 4 points that define this path. And then how pure pursuit smooths out these points is it draws a circle around the robot, which you can see in the bottom right, and it finds the intersection of the path and the circle, which is that blue point there. And that blue point is called the look ahead point. So instead of moving to the next point on the actual path, the robot's going to be moving towards this look ahead point. So when you get to a corner, the look ahead point is going to be on the second segment instead of the first segment. So the path automatically gets smoothed out like in the animation there. And some of the pros of pure pursuit is it's a lot easier to tune compared to trajectory following. There's only a little bit of PID that you need to tune. But a con is that it's less accurate compared to a trajectory, because the points that you give it originally act more as a guideline, and they're not actually what the robot is going to do necessarily. And I have a link down there that links to Peter from Gluten Free's tutorial on Pure Pursuit, which is a really great way of getting started with Pure Pursuit.
All right, so now we're going to talk about our team-specific autonomous programs and kind of what went in to making them consistent and high scoring. I think my team's autonomous is up first. Just a couple things you'll see before we play the video. The software I used to identify the vision target was Vuforia. We used odometry that allowed us to go from point to point on the field and follow those paths smoothly, which also allows the robot to recover if it takes any hits on the field. But you can go ahead and play the video. So you can see that it immediately identified the sky stone. It's going to go pick that up, and then it's going to be driving back and forth across the field as it starts to get the one other sky stone and one additional stone after that. And one important thing to think about when you're doing autonomous programming is also the path you're going to follow in terms of what's the best way to use your time, and how it relates to your strategy and how many points you want to score. That's just something you want to think about as well.
All right, so moving on is my team's autonomous. So for us, we used OpenCV at the beginning of auto in order to find the skystone. And then everything after that is just a pre-planned path made using Roadrunner. So as you can see, we go for one skystone right away. And then after that, the robot just pretty much just follows pre-programmed paths all the way.
So next up is my autonomous. And for my autonomous to detect the sky stones, we used OpenCV. So during initialization, it runs the OpenCV algorithm, and we already know during initialization where the sky stones are going to be. So as soon as we hit play, it'll instantly go towards the sky stones. And then for path following, we use the pure pursuit algorithm to move across the field and score the sky stones. So as soon as we hit play, it'll go for the sky stones that are already found during the initialization period. And then these paths that it's following are using pure pursuit. So we give it a few paths and then it automatically smooths out the jagged path.
All right, thank you for listening to our presentation. So now we're going to be opening it up for any questions you guys might have in Slido.
So it looks like we already had a couple questions that came in. Let's see. Yeah, so the first question was, can we just put a link to the slideshow in the Zoom chat? Yeah, we can do that.
Yeah, sure.
Just make sure it's shared with everyone.
Oh, okay.
The slideshow, yeah.
Oh, the slideshow? Okay.
Yeah. Let's see, the next question we got was, what is the best vision library, in your opinion? I think that depends on each team a little bit. I can speak for my team. What I found is I've used different libraries in different competition seasons. I've used both OpenCV and Vuforia. Vuforia is a lot easier to implement, and if you don't really require some of the extra features that OpenCV has, it might be the best way to go. Vuforia presented some challenges in this year's game, especially when it came to lighting and making sure you can see the target. But based on our camera placement and how we were looking at the image, we actually found it was pretty easy to implement. So we chose Vuforia over OpenCV in that sense. I don't know if you guys have any other thing to say.
Yeah, so my team, we used OpenCV this year because we've actually used it in the past before. Last season was the first season that I used it, and it was really effective because we were able to move these three squares over the last year's game. There was three minerals, two gold cubes, and one white ball. So we were able to move these three little squares over the minerals so that we didn't have to worry about whatever was around those minerals or the minerals in the corner. And we used that same tactic this year. We just put three squares over three of the stones so that we didn't have to worry about what was around it.
All right, so moving on to the next question. Somebody asked, would you recommend Android Studio to Unbot Java? So it really depends on what you want to do, personally, what you want to do. And a lot of it depends on whether you want to use external libraries, because the main thing about Android Studio is that it really gives you a lot of access to be able to use things like OpenCV or Roadrunner or any library that you may want to use to improve your autonomous.
I think another important thing to consider is, this might not apply to most of you, but if you don't have a high performing laptop, or if you only have Chromebooks available, as an example, Onbot Java allows you to use Java, but since it's all web-based, you don't have to download any external software. I know on Chromebooks you can't download Android Studio, or if you have a really old laptop that can't really handle the performance in an efficient way, Onbot Java might be a better solution than Android Studio. Yeah.
So another question is IntelliJ good for writing Java before you upload it to Android Studio? So Android Studio is actually IntelliJ based. If you open up Android Studio and IntelliJ, they look almost exactly the same because Android Studio is just a modified version of IntelliJ. So you do all of your code writing in Android Studio, and there's a button that you can push to upload that code to the phone. So IntelliJ is not really necessary for developing FTC software.
All right, looks like next question we have is, how difficult is it to program good odometry in terms of skill level and time commitment? It can be difficult. However, there are resources out there that can make it pretty easy. If you want to develop it on your own, there's a certain math that's required that makes it easy to develop. Usually, it requires some calculus concepts, but if you took pre-calc in school, that should be enough. It looks like my video cut out, but
Oh,
if you go back to the presentation, there was a QR code for an odometry video series that kind of walks through the software and even the hardware too about getting odometry hardware installed on your robot, but then also getting the software up and running. There's sample code that you can use and different ways to calibrate odometry on your robot. So there are resources out there to help you to kind of ease that process and getting it on there. Yeah.
So next,
and and then the next question. So somebody asked, what needs more work in terms of coding complexity, autonomous or manual? I'm assuming manual means teleop. So personally, I feel like autonomous definitely takes a lot more time and effort in order to program to work consistently. However, in teleop, you can use a lot of the same concepts that you use in autonomous in order to automate different parts and subsystems in your teleop code in order to help your drivers control the robot better.
Yeah, I agree with that. So even though the main challenge in autonomous is getting that really consistent or reliable performance, if you have a complex robot or in terms of hardware that's hard to control, if you can really make a lot of automated processes available in teleop for the drivers, it will help you control the robot, and as a byproduct of that, you'll be able to score a lot faster. So you can, like Ronnie said, you can bring over the same concepts into teleop um, to whether it's just like automating an arm moving or like a series of motions from servos. Using those same concepts, those same processes, and also implementing sensors in teleop is just as important as getting that same performance in autonomous. Yeah.
like an example of that this year is my team, we automated our lift and depositing mechanism. So we push one button and it'll go to the correct height, and then we push another button and then it'll deposit it. And then in between those two stages, if we want to, we can make any adjustments with our joystick. And then if the lift is in the air, the intake won't be able to turn on. So if the lift is up by accident, we won't be able to pick up a block and have it end up underneath our lift. So some of these automations really help us score faster, and they're really useful.
Mm-hmm. Yep.
All right. Next question: how do we keep rookie programmers involved? I think this is actually a great place where block programming can come into the picture. So I know a common thing on my team is when we're trying out different hardware prototypes or just trying to see how a subsystem works. Should we add sensors? Try those different things. Um, a lot of that programming can be done in block programming, and it's really quick because of the very simple user interface. And you can get programmers experience on that side by creating either just testing programs or writing software to develop or to test out prototypes. And then if you are using Java, either on-bot Java or Android Studio, you can transition it your block code to Java. But reality is you can keep your software in the block programming if you're not using different libraries and still have a really good teleop or autonomous program. Um, but it helps everyone on the team be involved in the programming and really changes the dynamic. That's what I've seen on my team, and just speaking from personal experience.
So the next question is, can you talk more about Pure Pursuit? Yeah, so Ronnie, could you go to that slide?
Oh yeah, sure.
So the way Pure Pursuit works is originally what you have to do is you have to input different points. So in the animation on the right, there's 1, 2, 3, 4 points each at the corner. And those points, each of those 2 points is just it's just a linear equation between 2 points. So then the circle around it, you can find the intercept between the circle and the line that you're on. And then that point that you get is the look ahead point. As you can see in that picture in the bottom right, the circle intercepts with the purple line, which is the path, and that blue point is the look ahead point. So the robot then moves towards that blue point, and every update, that blue point changes because the robot moved a little, and then the blue point's further along that purple line. So the robot's going to move towards that blue point, which is the look ahead point. And then if you get to a corner, the blue point might actually be on a different path segment than the robot's actually on currently, which ends up smoothing the path in the animation. And for example code, Peter's tutorial from Gluten Free, he has he walks through in a really nice way all of the steps that you need to get it working, and he also shows you how to interface it with his FTC simulator that he created. So if you want example code, he has some really great one on there.
Um,
So there's a question about whether I use Roadrunner or Pure Pursuit. I kind of used something that was similar to Pure Pursuit. It was a way to follow curved paths and also control the orientation of the robot as you're moving along. So it's very similar to Pure Pursuit. But right before the season ended, I was experimenting with Roadrunner. Um, Roadrunner is very easy to get up and running or relatively quickly, especially if you have an odometry system, and it's pretty easy to use. And it opens up a lot of things like Ronnie talked about in the presentation. It's personal preference. If you have the time to develop your own software or Pure Pursuit algorithm, go ahead and do that. But Roadrunner is still a great library you can use to get those same results.
So next question is, what encoders and wheels are you guys using for your odometry pods? This year, my team used the US Digital S4T encoder. It's a pre-built encoder, so we didn't have to assemble it. And then we just used the Go Build 2-inch Omni wheels. And then we have a 3D printed case that goes around it that combines the encoder shaft and the Omni wheel. And that's all in a linear slide with a spring on it.
Yeah, my team, we also used the US Digital encoders. We also had a 3D printed mount that we used a rubber band to spring load it. That way, when you're driving across uneven surfaces, the odometer wheel can go up and down to kind of maintain contact with the ground. If you go back to the presentation and look at that QR code, there's a link to those encoders and some of the 3D printed files that my team used.
all right, so next up, somebody asked about how much knowledge is needed in Java. So I feel like you need to have like knowledge mainly about the syntax of Java, and you also need to know about like inheritance and like most of the object-oriented programming stuff in order to be able to like effectively use Java. But you can also just program like most of your stuff inside the like linear op mode or like inside just an op mode class by itself.
Yeah, and there's certainly some features if you have some advanced knowledge of Java that you can take advantage of if you're trying to like build like a proper structure or hierarchy to your development. But it's not necessary for building good autonomous programs, I don't think.
And somebody else asked if how you program different actions during a path defined by Roadrunner or Pure Pursuit. So I'm not sure about, so if you're following a path, right, chances are you're probably using a while loop. So inside that loop, you could add a condition to do some sort of action like moving your elevator or activating servos, especially if you make it so that you can run all your code at the same time, like you're able to update your elevator subsystem and your drivetrain at the same time. That would be really good for being able to like using elevators and arms asynchronously with your drivetrain.
And yeah, same thing for Pure Pursuit. You can have a condition inside that main while loop. Or another simpler option is just have two paths. You do path one, stop, do your action, and then do path two. In the case of servos, if you want to make that gap really small, you can get rid of the delay that you normally have with servos, because the way a servo works is if you tell it to go to a certain position, you're only commanding it to go to that position, and it still takes time for the servo to actually move there. So you can have that motion happen while the robot's moving in another path.
Mm-hmm.
Do you guys have any suggestions about that?
No. Personally, I have not done odometry. I've only done odometry on drive encoders. Sorry.
So I've done odometry, three-wheel odometry. I've never done two-wheel and IMU odometry. But with like three-wheel odometry, a big thing is getting the measurements really, really accurate, like the measurement in between the two of the encoder wheels and the distance from the center of your robot to the back omni wheel. If those measurements aren't precise, then you're going to get a lot of error accumulated. I don't know how necessarily how you setting things up with Roadrunner because I've never used Roadrunner, but yeah.
I think if in Roadrunner there are a couple constants that you kind of have to tune in order to get it to work properly. So I would just spend a lot of time making sure that you get things like the track width, the encoder counts per revolution, get those things right, and then you'll be able to make sure that you're getting accurate readings. There was on the GitHub repository for the Roadrunner Quick Start, there was a issue thread about how to get that working well. I'm just going to put it in the chat for you guys, but that should help.
Yeah.
Right, next question, how do you deal with the going over the neutral bridge? That's something my team didn't really deal with until very late in the season. You can create a mechanism to lift up the odometry, since if you create a spring-loaded system where it can go up and down, if you have a servo that can kind of just lift it up off the ground, that kind of mitigates any risk in terms of breaking it. Since it's most common not to use odometry during teleop, my team does it, but most teams, from what I know, most teams don't. So after autonomous, so during autonomous, you can have all your wheels on the ground. But in teleop, what my team did was, if you have your three wheels, we had the one wheel that was parallel to the edge of the neutral sky bridge, that third wheel. We had that lifted up off the ground. And then when driving over the sky bridge, the neutral bridge, we could only go in one direction, but the wheels just pop off the ground and pop back down since we're using that spring-loaded system.
My team, we have a spring-loaded system, but the physical stop of the actual slide is high enough that we can just go over it without any problem. Next question is, where can you find pure pursuit? I don't know what you mean by like find pure pursuit, but there's a lot of resources out there. Like Peter's tutorial from Gluten Free, that's by far the best one that I found to help people get started with pure pursuit. It's really comprehensive. He walks through all the math behind it and how to find that intersection point and how to change the look ahead circle so that if you want a more fine, more accurate path versus a more rounded, faster path.
For the question about seeing the Vuforia target, so my team, we used the phone camera, but there are actually some adjustments you can make. So we had some problems getting good lighting and getting enough zoom on the target. So if you use a phone camera, you can, there's a zoom feature built in the Vuforia library that you can use to get a close-up picture on the camera, or sorry, on the target. And you can actually also turn on the flashlight on your phone to light up the target, which is something that we did. An alternative solution would also be to put an LED strip on the front of your robot to kind of light up the target again, so before you can see those key features. And that's how we were able to see the target without moving closer. So you just zoom in to get that same effect.
So the next question is there any way we could see code samples or code examples be sent out later? Personally, our code is all on GitHub, and you guys can definitely just go take a look at it if you want to. There's also a lot, Peter's tutorial, as Kavish said, is a really great resource for learning about peer pursuit.
All right, next question is about the field targets being used for robot orientation. I've personally never used the V4A targets for determining the robot's orientation, since that partially depends on the orientation of the camera and its location. So you have to go through the process of setting that up. I've just used the IMU installed in the RevHub. I find that's the easiest solution since it's already pre-installed hardware on your robot. It's really easy to set up, I think. Yeah.
Mhm.
So next question is, doesn't Roadrunner use another language for the part of the library other than Java? Yeah, Roadrunner uses Kotlin for a lot of their library, but don't worry if you don't know Kotlin. That's all internal things that Roadrunner deals with. So all the way you interface with Roadrunner, you can do with Java or Kotlin. So you don't need to have any experience with Kotlin to use Roadrunner.
And I think, so there are a lot of examples that are built into the documentation for Roadrunner. They're all in Java. Well, you can actually see them in both Java and Kotlin, I think. If you're unfamiliar, you can go through that documentation and it should really help you get familiar with what's going on.
So the next question is, where should you even start when learning how to program autonomous? So personally, I started by learning about Java and then really just reading through the examples in the FTC SDK. That really helped like get me started on how to actually write code.
I think an important thing is just getting familiar with the FTC kind of programming environment. Start out by programming Teleyop, kind of driver controlled things, trying out different operations with motors, servos, getting readings on different sensors. That's something that's really easy to do in block programming, but you can also do it in Java. And kind of once you get an understanding of the different capabilities or kind of sensor readings or things you can do with motors and servos, you can start building that together to create an autonomous program. Yep.
What is the main difference between Pure Pursuit and Roadrunner? They're actually really different. So Roadrunner uses motion profiling and trajectories to follow the path, versus Pure Pursuit just uses points that are more of a guideline. And the difference is Pure Pursuit requires less configuration compared to using Roadrunner, but it's also a little bit less accurate compared to trajectories, because the robot's going to follow that trajectory almost exactly, versus with Pure Pursuit, the original points you give it, the robot's probably not going to follow them exactly, especially in corners.
Another thing I'd like to point out about Pure Pursuit versus Roadrunner, Roadrunner is more of a like path planning library that doesn't, it also includes like many path followers, while Pure Pursuit is just a path follower.
Yeah.
So next up we have, do you know if there are any samples for motion profiling and trajectory for Roadrunner? So definitely if you go to the Roadrunner GitHub, you can find the documentation on their, you can find their documentation, and there's a lot of examples there on how to make a motion profile and trajectory. And also if you take a look at the Roadrunner Quick Start, there's also a lot of useful resources there about how to get Roadrunner set up and also create motion profiles and trajectories.
So next question is, do you have any example code for Pure Pursuit? So with Pure Pursuit, the best way to get started with that is not to just look at the code, but to understand the math behind it. And for that, again, I recommend Peter's video. He walks through from the very beginning how to do the circle line intersection in Java, how to program all that with the look ahead point, a look ahead circle, and he does a really good job of walking through how it works, not just giving code for it. So, and then he does have code for it at the very end.
There are also a lot of papers you can read. There's one from Carnegie Mellon that comes up a lot when it comes to using Pure Pursuit. So if it's important to understand like the background behind it. Yep.
I'm having trouble actually learning Java. Any tips on how to understand it? So there's a lot of resources out there. Code Academy is one of them to learn Java. And if you want to learn Java, probably don't start necessarily with the FTC SDK. Start with just learning plain Java, learning the different structures and syntax, if statements, for loops, while loops, things like that. Without the FTC SDK mixed in. And then once you get solid understanding with things like if statements and for loops, then start going into the FTC SDK part of things.
Yeah, I think when it comes to if you're having difficulty crossing that bridge of just Java only combine and Java with the FTC SDK, if you try using block programming, there's an export to Java function, so you can see how different things that you're doing in block programming. Since you can see that visually, like the different if statements, while, and for loops, you can see how that visually translate into the language, into Java language and text.
So next one is, what encoder am I using for odometry? I'm using the US Digital S4T. I'll put a link to it in the chat. It's really nice because it comes pre-assembled, unlike the E4T, and it has a shaft built into it. So we just made a 3D printed hub for it that attaches to the Go Build a Omni wheel.
And next up is, how much time do you spend teaching the basics to your rookie programmers? Personally, I've never actually taught anyone the basics. So if you guys could like give some.
This is something I've done for a couple seasons. So the most important time to do this is during the summer, because you don't have the rigors of a competition or kind of these deadlines you have to meet to get your robot ready. So I would definitely take advantage of getting together during the summer. You can use previous competition robots or just some basic robots to kind of teach, first of all, how to connect the phones, configure robots, and then start teaching some of the basic motion or kind of the basic actions like setting motor powers, putting servos into positions, using sensors, and then kind of putting all that together when it comes to building either a teleop or autonomous program. So that time during the summer is really crucial to getting that done. And then once the season starts, if you can have your more experienced programmers work with the rookie members to kind of see the process that you go through when developing software, or kind of the different algorithms or math you have to go through to get things done. So you have to start in the summer and kind of transition to that and work together, like in pairs or something during the season, to kind of teach your skills to the rookie programmers.
So exactly what do you need to do to prepare for teleop? I'm assuming by prepare for teleop, you mean like code-wise, not in the 8 seconds in between auto and teleop. But to prepare for teleop code-wise, one of the main things is if you have some servo combination or something that needs to, multiple servos that need to do something that happens more than once during teleop. Like this year, a common one is depositing. A lot of people have multiple servos, like one hinge and one grabber for the block to deposit it. Automating that type of thing is really, really going to help, so that you don't have to push multiple buttons when your lift is in the air to deposit the block. And also making your lift go to automatic height, automatically go to the correct height. It's also really useful, so you don't have to manually be lifting that lift to the proper height. And if you miss, then you might topple over your tower.
I think this might not be what the question was asking, but when it comes time to like writing your teleop program, one of the things I've noticed is that a lot of times in like the driver station boxes, like when I'm volunteering, I see this. There's sometimes teams that argue about the controls or what button presses what. I think it's important to, as a software person, to work with the drivers to make sure they get the controls they want, because in the end, the drivers are the one controlling the robot. So you want to make sure that it's pretty easy to control the robot, which requires some collaboration with the drivers.
Oh, I'll share the slide link right now. Sorry about that.
Do I have any Pure Pursuit example code? Peter from Gluten Free. His code is very good, and he walks through how it all works from the very beginning. Yeah.
So next we have the expansion hub is bad at slowing down the motors. They don't break walls. Ours overshoot even with trapezoid profile. So there could be a couple things that are causing this. It could, if you're using the motor velocity PID, people have said that there are problems when you're trying to run them at a low velocity, especially when it's really close to zero. So that could be the problem. Or you could have too high of you might need to tune your feed forward constants a little bit better because they might be slightly off, causing you to overshoot.
Where should I start when trying to learn coding for the robot? So the FTC SDK has a lot of really good examples that you can look at that run through how to set power to motors, how to set power to servos, how to get back sensor data. So looking through those so that you can understand the syntax of the FTC SDK is really useful. And then once you do that, just making some test programs, experimenting a little bit with making a test chassis or just getting data back from a color sensor or distance sensor is really helpful.
Yeah, so you want to kind of play around with all the different things that you have available to you so you can start putting together those things to build up either a teleop or autonomous program. And there are actually some videos on the wizards.exe YouTube channel that Arjun made. He's another one of my team members. It's for block programming, but it walks through some of the basic things you need to know when programming a robot. So that might be useful.
Next one is, what odometry wheel am I using? I can put a link to it. It's the 2-inch Omni wheel from Andy Mark. It's the compliant Omni wheel, the new one that they have. So let me just put in the chat. They're really nice. We haven't had any problems with them or anything. Yeah, and then we use it with the S14 encoder.
All right, so the next question is, if we already know Python, should we start off by learning the syntax, or would you suggest learning something else first? I think learning the syntax is definitely really nice, along with getting familiar with the SDK and learning about how to use sensors and setting powers to motors and all that.
Yeah, I'm guessing if you know Python, you know some of the basic logic things that kind of just apply straight over to Java. So it's just a matter of learning a syntax is something that kind of goes quickly if you already have the experience programming in Python.
Next one is, do I have a picture of my robot that I can share? I do. I'll put it in the chat. Yep.
So next question is, thanks for doing this. And my question is, how did you guys even start learning Java? What did you use? So me personally, I learned Java off of Codecademy, and then I really just like jumped into learning about all the stuff in the SDK in FTC.
So for me, I had a little bit of knowledge with Python beforehand, and I kind of just jumped into Java. I probably shouldn't have done that. I probably should have focused more on some of the fundamentals of Java so I could learn about object-oriented design and stuff. But I just jumped in and started working with the FTC SDK, and I learned as I went, which in hindsight wasn't the best way to do it. But yeah.
I did the same thing as Havish. We actually had a mentor who knew Java, so she kind of taught us the fundamentals of Java programming. But a common thing that I do is you take what you know into the FTC season and kind of build on it a little bit. But then during the summer, you can take the time to either learn object-oriented programming or some different libraries you can use to make your programming design or structure easier or more efficient. So you can kind of really improve on what you already know during the summer to kind of up your game for the competition season?
Do I have a picture I can share of my odometry pod? I do. I have to find it, so I'll put that in the chat once I do.
So next, somebody asked, by default, is Roadrunner set up to use 3-wheel odometry, the motor encoders, or something else? So Roadrunner is set up to use the motor encoders. However, you can pretty much use any odometry setup you want as long as you just input the position that you get from your odometry into the controller that you use in Roadrunner.
Yeah, Roadrunner is designed to kind of help you build software for whatever your robot looks like. So by default, it's just encoders, but you can add in, they have a class for either 3-wheel odometry, or I think they also have one for 2-wheel plus IMU. So you can put that in there automatically and kind of takes advantage of that.
So next one is the syntax for the robot coding different than normal Java? It's not different, it's all still Java, but there's a lot of functions and things that you have to learn what they do, like setting power to motors or getting data from sensors. Things like that. There's a lot of things that you have to learn with the library, but it's all still Java. So the syntax between like calling a function in Java and calling a function of the FTC SDK is the same.
Mm-hmm.
Am I planning on releasing my Pure Pursuit code? No, not currently, because it's really messy. It's not easy to get working with any other robot besides ours. It's kind of hard-coded, built-in with the way I have things done on my robot, and it's not really going to be helpful to other teams.
Yeah, so if there's no more questions, I just want to say that thank you so much for coming. And also don't forget to fill out the feedback form, which was just posted in the Zoom link. Yeah. Thanks so much, guys.
Thank you, guys.
Thank you.